So welcome back, Level 3 physicists, continuing on with the electromagnetism, electricity, external. Today looking at capacitors in alternating current. So in terms of resistance, resistors as components in AC, in a circuit containing only a resistor, the current and voltage are in the same direction. They're known as being in phase. Therefore, to work out the current or voltage at a particular point, we can use the equations for rotational motion. Okay, so the voltage across the resistor at a point in time will be the V max or V naught, just interchangeable there, sine omega t. And the same for the current across or going through the resistor at any particular point will be the I max, seen here as I naught, sine omega t. Okay, so in terms of the capacitors though, things start to change. So when a capacitor is placed now in an AC circuit as opposed to a DC circuit, it will start to charge just like it would in a DC circuit. But then in AC circuits, the current changes direction. So that means the capacitor can now repel charges in the same direction as a supply current. Okay, as you can see in part B of the images on the right. Okay, so charges flow in the circuit. Okay, but no charges actually cross the capacitor because now you've got that repelling as the charges build up. At the start, there is no voltage because there's no potential difference. There's no charges on no charges being formed on each side of the capacitor plates. But as the charge begins to flow, the voltages increase and current begins to flow. Then, because you've got this buildup of charge on the plates, the current reduces to zero as the capacitor fully charges. Okay, so when you've got maximum voltage, you've got zero current. When you've got zero voltage, you've got maximum current. Therefore, the current and voltage are not in phase. The current is 90 degrees ahead of the voltage. That's what that actually just means. So in terms of capacitors, okay, so the energy supplied in the capacitor is due to electrical field being stored in the plates and returned during discharge. There is no discharge in AC, so therefore there's no energy being dissipated. Therefore, capacitors aren't technically resistors because resistors dissipate energy. So that means we have a new term called reactance. So reactance is effectively the resistance of a component in AC. And so for a capacitor, the reactance is 1 over omega, the capacitance, okay, where the reactance is measured in ohms because it's effectively a resistance. So the RC circuit in AC, the AC circuit on the left contains both a resistor and a capacitor. Okay, so the resistor is not going to be affected by being in an AC circuit, but the capacitor will. Okay, so now you're going to have a total resistance, which is known as the impedance. Okay, and it's also measured in ohms. It's not really a total resistance because the capacitor is not a resistor. But basically the impedance is the total resistance of an AC RC circuit using Ohm's law. So you can apply Ohm's law. So the supply voltage will essentially be equal to I times Z. And this impedance can be calculated because for a resistor, as we've seen earlier, the current and voltage are in phase, but now for a capacitor, the current now leads the voltage by 90 degrees. So you can set up a vector diagram as shown. Therefore, the voltage across the resistor leads the voltage across the capacitor by 90 degrees. Okay, so that means you can have VC going down. Okay, the voltage across the capacitor 90 degrees out of phase with the current that's running through the resistor. And also the voltage running through the resistor. So how do you calculate impedance? You use Pythagoras in trigonometry to set up a right angle triangle. So Z, the impedance, will essentially be the square root of your reactance of the capacitor, all squared, plus R, the resistance, all squared. And analogously, the supply voltage will be the voltage across the capacitor, all squared, plus the voltage across the resistor, all squared. Okay, so the phase angle will be tan theta x c over r, and which is analogous to VC over VR. So you can use that. That phase angle is an illustration of how the impedance or the supply voltage is out of phase with the current. Okay, so now we'll move on to the inductor.